Hey guys, well, what's going on? Memes here. This. We're back. We're gonna do some other stuff and things. I posted a little video the other day. Was it Anastasia and Shiloh from over at the Demystify Side podcast? They had their first episode of Paradigm Drift recorded a couple of weeks ago. Full episode should be coming out on Thursday. I posted my little segment. Uh, it's about like 10, 11 minutes, something like that, where I was going on kind of this explaining how basically it was kind of like a Shark Tank for different theoretical models and stuff like that. I kind of just went over the whole claim of, well, you took a look at the Higgs mass divided by the Planck mass, you get a number. Didn't really make that much of it. However, if you square it, you at least get the first three digits because, to be fair, we only really know the Higgs to about three significant digits, about 125 giga-electron volts there. So the whole claim is, well, if we know h bar to 10 digits, it's literally defined there. The Planck mass is currently known to five significant digits. Maybe we could leverage a couple extra significant digits to try to predict it. Lo and behold, to my shock, is you can't even call it a prediction because it's already been measured at that level. But hey, Chris, good to see you, my friend. Good to see you, my friend. But that's not specifically what we're talking about today. So we're going to be talking about some fun stuff. We're going to be talking about the golden ratio. And the golden ratio is an absolutely fascinating thing. People have been talking about it for, God, probably millennia or so now. So let's just go into that real quick. So, God, no, no, hold on. Okay. Oh God, I'm selling away my privacy to share a screen. Oh dear God. All right. The golden ratio. What the heck is the golden ratio? All right. Our mathematics, two quantities are in the golden ratio. If their ratio is the same as the ratio of their sum to the larger of the two quantities, basically it's this thing here. If you get A plus B, you divide by A. Whatever the heck that is. So you have like that, and then you're going to get the ratio of A to B. And that equals phi. Okay. It's the Greek letter phi there. Okay. So it's got all these cool constructions. It's also the minimum nested radical, because do they have it here? It's basically if you do the square root of one plus the square root of one plus the square root of one infinitely, you get the golden ratio. Yes, it's all over the place. It's within the Lucas numbers, the Fibonacci numbers, blah, blah, blah. All these crazy things. I don't know. People like to get, I don't necessarily want to say occultist like, or I don't know, maybe it is straight up into the occult, but it also has a lot of uh, cool mathematical relations. Why am I showing you any of this? Although, basically, aside from, well, there's a lot of cool stuff that at least approximates the golden ratio. There, often people will say this is the golden ratio. Certain things like, oh, the Mona Lisa used the golden rate. Or it's used in architecture. And people will say those claims, and maybe some people do, but ultimately it's like, is it really the golden ratio? No, it's kind of close, but they go works because, well, if you're an engineer, you're going to do engineering. Okay. So that's cool. All right. Why am I showing you this? What the heck is the point? All right. It was given away in the thumbnail if you blow it up close enough. So let's just erase this now. Although the folks perhaps join, I know there's a lot of potential circus going on this evening, let's say. I kind of checked out of that. I pay attention. I see some of the memes, but as far as losing my mind over everything that's happening, I'm going to reserve losing my mind for appropriate situations. Otherwise, well, my mind would have checked out a long time ago. Some may claim, and it's not unfair, that my mind has checked out a long time ago, and well, whatever's here right now is something, maybe. I can see I left it up for too long. All right, it's okay. We're gonna kind of pipe the same thing. So what are we doing here? All right. So we're going to put our claim here. I'm going to spell it out explicitly. So literally, I forgot to put the links in there. I'll toss them in later or something. But the whole claim is, okay, so if we were to take the elementary unit of action, so we got our little friend here. We got our H. And we got that little bar thingy on it. Okay, so we got H bar. God, it looks too crazy for my own liking. There we go. H bar. Okay. Boom. All right. And then we're going to divide that. This is expressed in joule seconds. Joule is a unit of energy times seconds. What ends up happening, that gives us a mass, area, rate, yada, yada. It's a unit of action. Okay. So we're going to divide it by the dimensions of action. And that's joule seconds. Cool. All right. So we got that, and that's going to give us, since that's in the dimensions of action, that's in the dimensions of action, it's going to just come out to be a dimensionless number. Okay. This may actually even make more sense. A lot of it was just a calculation. And I was asked, I think I started like, what's the interpretation? Now, you got to be careful, because I think what happens is, and I've totally done this myself, but as you start to actually go into things and you're like, oh, maybe there's actually something here, it tends to get a little bit more conservative with some of your language, because it's like, if you're gonna hold on, let me finish writing this on the board. Okay, so the whole claim is the elementary unit of action. When we divide it by the dimensions, literally the ones of action, joule seconds, that should equal the mass of the Higgs, m sub h, over the Planck mass, which is m sub p for Planck. And we take that whole expression, we throw in our protective brackets, and we square it. The claim is that this should be equal, because this gives us, basically, this is in mass. So if you were to literally just cross this out, solve for x, throw your kilogram tag there, you're going to come out to the Higgs boson mass. It's the Atlas results, it's about 2.3 sigma. The CMS current results, it's about 0.2 sigma. Because this is going to come out to be approximately 125.37 GeV. GeV. Okay. If you look at some of the CERN measurements, it's been measured at 125.38. I think there's at least been one or two measurements where literally, at least some paper, I think a couple papers on the archive, actually, the analysis was like, we see it as 125.37 GeV, but those papers at the time had like a 2, so it's 20 after the decimal point, so it could be up or down, but it literally has been measured of that. It's float around. Oh, cool. Dude, the LLMs are amazing, and I think you can kind of groom them, so to speak. 'Cause, yeah, you got to be careful, because if you ask something, it's kind of like a person. You can lead somebody down a trail of thought, especially if somebody happens to try to be agreeable. A lot of times they'll kind of. One of the things that got me with this is because I was using Chat GPT earlier in the year, and even one of the fancier versions, I'm like, oh, I just want to say things, and then I use the Wolfram plugin because it tended to be more conservative. It's like, oh, you're gonna need more things, and then it's started saying nice things about this. I'm like, really? Okay, maybe let's explore this a little bit more. Okay, this is not why we're here today. This is just where's the golden ratio memes? You've been talking about this. You used this little silly thumbnail. All right, let's get into this. So before we get back into the board, let's go to our friend over here. All right. Back to this window. All right. So the Electroweak Epoch. Why am I showing this? We're talking about Electroweak symmetry breaking. Okay. The whole reason why is In physical cosmology, the Electroweak Epoch was the period in the evolution of the early universe when the temperature of the universe had fallen enough that the strong force separated from the electronuclear interaction, but was still high enough for electromagnetism and the weak interaction remain merged into a single electroweak interaction. Above the critical temperature for electroweak symmetry breaking, which is this number right here, 159.5 GeV plus or minus 1.5 GeV in the standard model of particle physics. Okay. So people have different ideas. This is the number you're going to typically find in everything here. Okay. I never really paid attention to that number at all. Why? Because we only know it to one significant digit. Why? Look, this is the error over here, that 1.5 GeV. So let's suppose you did plus. That's going to be 161 GeV. If you subtract it, 150, 58. Okay. The problem is we only know this to one significant digit technically. Why? Okay, we got 4 digits there, but you get error in the last two, and that might flip that up to a 6. So that's why this is considered more of a fringe science video here. I thought it was kind of cool. But keep note, it has one significant digit of agreement. Then again, there was a non-insignificant period where we knew the speed of light to 0 significant digits. It looked like a 3. It's 2.9979. So, I mean, I don't know, at least in elementary school, they told you to round up. So, okay. So why am I showing you this? Okay. The reason why I'm showing you this is because of this. Okay. So we take our same equation. Actually, no, let's do this. Okay. So this right here, that H divided by seconds per joule, or per second joule, that's just joule seconds. They just write it in the other form there. So we're solving for X kilograms, divide by the Planck mass squared. Okay, we got all that. What's this little friend here? Oh, wait a second. That looks familiar. Wait a second. Oh, well, never mind. It's the golden ratio. Why? Because it is. So, what do they call it? It's phi. Yes. Okay. Phi. There we go. I always confuse phi and psi. I want to get the terminology correct. Let's. Oh dear God. I didn't say by modifying the embedding inputs using. See, that one's surprising. Some of these AI models are all over the place with different things. I've seen some really cool things. Heck, one of them at one point was so convincing. It told Stephen Wolfram, he's like, "Tell me about a blue wolf," because there's no such thing as a blue wolf. And then it went to this elaborate description. Well, there's a rare Tibetan wolf upon these plateaus. It was actually as convincing enough that it's like, is there actually a blue? There was no blue wolf. Spoilers. Okay. Where do we go over there? Okay. The whole point of this, let's see, is okay. So we just take our exact same expression. We literally just divide it by the golden ratio. Scroll down. It gives us the number. And again, note there is a positive answer and there is a negative answer here. Okay. Again, people have invoked that, there's no negative masses or stuff like that. And again, I could just use absolute brackets or something like that, but I don't know. Maybe it's trying to tell us something. Again, I'm not a licensed quantum mechanic or mathematician by trade. I'm a dude on the internet like a lot of y'all. So just happen to be curious. So when we take that number there, note there, that 2.843 times 10 to the negative 25. So we go up here. We're solving for kilograms. Okay. So we can add the kilograms in there. And then we want the mass energy conversion. So we multiply by c squared equals mass times c squared. Boom. Cool. Hey, Tommy. We're talking about how some perhaps Some of the most interesting geometry and perhaps the simplest, I don't know, continued fraction might have to do with electroweak symmetry baking. So yeah, we got our golden ratio here. We literally take our old expression, we literally just divide it by the golden ratio. Okay. What do we get? Oh, 159.5 GeV. Wait a second, that can't be right. That's this number here where it says the electroweak force and electromagnetism broke apart. That's the breaking of the weak force. There's no way the golden ratio can be involved in our physical universe, so to speak. That would just be weird. Kevin, I'm not gonna lie. A lot of the AI, you go through it, it reminds me a lot of conversations I've seen on the internet. So a lot of that one surprised me. But I digress. Listen, we're going to use it as a tool. It's a tool. If you're trying to use it as an oracle to solve all, maybe we'll get there at some point. Can't say. But it's a fascinating thing. Ah, cool. No, if you got a video or paper or something on that, I'd like to see dark matter. My base assumption is just old cool matter. That's my best estimation there. Personal opinion though, could be totally wrong. Okay, so we got this number here, the electroweak interaction. It breaks at this number here. Wait, you mean this number here that we get when we get our little estimation for the Higgs mass, which, to be fair, that actually, let's pull this down. Okay. So this is the whole thing. This is at least one of the things that I went on the paradigm drift little thing where they said I at least had confidence to show it why. It's technically already been measured there, so it's kind of a retroactive explanation. Uh if you want to take the extreme charitable and kind of be a dick rote, you could have just gone in and be like, "Oh, so what are you showing us today, Mr. Memes?" It's like, "Oh, I've solved the hierarchy problem." Kind of an over the top statement. But when you take, actually, let's just do this. Let's stop that screen. We'll go to here's why we make videos of things, because it can better describe things in the way I had it before. So let's go over here. Okay. Present. We'll do this little 90-second video. Okay, go here. Okay, as we can see, you cannot predict the Higgs mass.
The hierarchy problem. And it's important because its solution is going to lead us beyond our current theories.
What's known as the hierarchy problem. That's the question of why the mass of the Higgs boson is so much smaller than the Planck mass.
The hierarchy problem, put simply, is that we don't understand why the mass of the Higgs boson is so small.
Okay,
the mass of the Higgs boson is a constant of nature. It's one of those three parameters in the Standard Model. This means you can't predict it. You just go and measure it.
From our understanding of quantum field theory and the Standard Model of particle physics, interactions between the Higgs and the quantum vacuum should drive its mass up to enormous values. That would be catastrophic for our universe, and so we should be grateful that the small Higgs mass is somehow protected. We just don't know how it's protected.
Supersymmetry doesn't change anything about this. The Higgs boson mass is still a free parameter in supersymmetric extensions of the Standard Model, and you still can't predict it.
That's interesting.
You may say, well, why not? And indeed, there's no reason why not.
Couldn't resist, mate.
Listen, I'm just saying, I don't know if any of this stuff is right. I'm just a dude on the internet. I'm just a bag of bones, flesh, and stuff like that. And most things are wrong. But if the question is, why does the Higgs mass so much smaller than the Planck mass? And then if you delve into one of Professor Carroll's Mindscape interviews with Dr. Cesarati, I believe her name is, she said it's actually, no, it's not the relationship lie between the Higgs mass divided by the Planck mass. It's actually the squared relationship between the Higgs mass and the Planck mass. I don't know about you all, but at least to me, as a dude on the internet, I'm like, well, what if the Higgs mass takes the mass it does because its mass divided by the Planck mass all squared is tuned to the magnitude of the elementary unit of action h bar. Therefore, the Higgs takes the mass it does in order for the unit of action to act. I don't know if that's a good explanation, but that's an explanation I can at least start to follow. I'm like, okay, if you got all these blocks there and we need to have a certain, like, I'm just thinking about cars because I used to be into cars. You need to have a certain precision for your cylinders and stuff like that. You have certain tolerances, otherwise the thing ain't going to work. So things need to fit together in a particular way. So if that's the hierarchy problem, I don't know if this is a solution. I'm sure there'd be more fancy things. You need to get the what's it? Because was it they have like a four components Higgs. When you actually go through the actual like quite again, I'm not a quantum mechanic, but they're breaking it up and so you get some stuff over here. These things are bracketed. We're squaring this. We're taking the absolute value and everything. Listen, I'm a simple dude. For me, I'm like I go into the computer. I type some numbers, or maybe just type in the words because you can actually just break off this part, type in h bar, divide by joule seconds, put the parentheses there if you're going to just do the division there, because otherwise it'll break second into multiplication rather than division. But literally, so that equal to the mass of the Higgs divided by the Planck mass squared, and will tell you it's true. I had to send them an email just because I'm like, no, we can't say this is true because you're doing rounding because we only have so many significant digits. So, but it's easily a falsifiable prediction. So we get another couple high precision digits for the Higgs, we'll be able to say, yeah, you know what, there was nothing to this. We're totally barking up the wrong tree. Or maybe they'll show us some more significant digits and maybe it's an interesting thing worth exploring. I don't know. Let's get back to see what we got. Blah, 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 blah. No, what is mass? That is a great question. Hey, Jack, what's going on? Again, perseverance. Solid. Oh, Jax, I think we're gonna do that tomorrow. Um, there's something called maximum extendability. So this is something I think Thad has been talking about for a while, but apparently it's actually kind of a known thing where basically if the claim is universe, so to speak, I prefer a realm of persistence, but colloquially we use small u universe is as big as it can be. Therefore, basically, if you were to take this, is if you believe that things continue infinitely small, then things would be infinitely big. You're literally taking the inverse of that. However, if there was something like, I don't know, an elementary length, like the Planck length or something, you were to take its inverse of that in its same dimension, aka you do meter squared over Planck length. Perhaps that's a maximum of some sort, maybe a maximal radius to our end hypersphere of maximal volume. I don't know. Uh okay, so let's get into the whole what the heck are we saying? So the claim is that this is the mass of the Higgs, and then how do we write this? Let's just write it like this. So we'll just do the exact same thing. So I'm just gonna go do h bar, a little bar, divide by joule seconds again. Okay, we got joule seconds. And then this time, oh, we're gonna get so dang fancy. I mean, look at what we're gonna change up. We're literally gonna do what is it? Electroweak. I don't know, how would I even say that? How would I abbreviate that? Let's do EWSB. EWSB. All right. Because we can, so all right. Electro weak symmetry. Oh, screw that. I'm just gonna write the letters. Too messy for my taste. E W small SB. Electroweak symmetry breaking in kg. Okay. Divide by the Planck mass, m sub p. I'm gonna square that, and then we divide the whole thing by the golden ratio. And that gives us 159.5 GeV. Do I expect this to make it into textbooks? No. I mean, the Higgs mass, since it's already been measured and you see the measurements around it, yeah, we at least got that to some significant digits, and we at least got one experiment it's well within 1 sigma. This, again, you get still 1.5, so we only really know it to one significant digit because that could become a 6 in the second one. So it's in the ballpark. We're just going to need better measurements. That's ultimately what it comes down to. We're going to need better, well-designed measurements to see what we got. I was just curious. I just like, because you can actually use this number and then also conjecture it again. A little bit less confidence. This just seems simple to me that I can try to start to intuit. But if you take this math for the Higgs, you can actually, we did on some other videos, can calculate or at least conjecture the masses of the Z boson, the W boson, as well as the top quark. Coincidentally, the ratio from the Higgs mass to the Z boson is basically, at least appears to be, the same ratio between the Higgs and the top quark, which is a very interesting thing. Because I was trying to solve for that because Thad had found what he believes a good fit after they updated the codata measurements for they call it the weak mixing angle. He found a closed form for that. So I'm like, all right, if we were to assume that was correct, and again, these are a series of assumptions. We're building up our theoretical ladder, our ladder of logic. Now, the big thing is you can get any number you want. You can, and you'll see some things. So sometimes you'll go and you'll see somebody, it's like, wow, all their data matches everything perfectly. And then you get suspicious because really, all the data fits perfectly? Maybe it is. Maybe they've solved everything, or occasionally, listen, I just sometimes make mistakes. I've literally, like I was reading a paper earlier where like, I think this is just wrong. I think these is some type, or I think it was on the archive, so it was a preprint anyway. So not a huge deal. But if we were looking at these things and you're like, all right, well, maybe there's some relationship between it. But long story short, just for this is if you look at it, you're like, all right, I was just trying to look to see. I'm like, well, if we got this number, what's what's the difference there? And then you divide it. Oh, let's just do that right now. This is literally what I did. I think I maybe took a few more significant digits, but let's get a friend over here. Okay. So I can run more. Okay. All right, now let's just do this. All right. So what do we have there? We have, all right, so let's see. 159.5 GeV divided by 125 point. We had 37 GeV. Okay. So I looked at this and I'm like, okay, what is this number here? What might be going on? Okay. So I look at this. So we take that number. Let's look for that number. Oh, no, no. Don't want all. It's automatically filling in because, yes, I've totally searched for very similar numbers before. Oh, that's interesting. Okay. So, okay, so it gives you potential answers. Wait, what's this? Oh, all those numbers happen to fit the square root of the golden ratio. That's kind of cool. So, long story short, because basically, if you were to just take that initial number that we had there, so if you take this number for the Higgs here and just do the square root, and just literally type golden ratio, we get to it there. All right. I mean, that's a very interesting thing. At first, I looked at this, I'm like, oh, that looks kind of like close to 1/2 pi. So I was trying to figure out if maybe that was something there. And then after a bizarre amount of calculations and numerology, I'm like, all right, you're looking for simplicity there because you can kludge anything. You can add epicycle, adjust this factor, throw in this random factor. But whatever you do, you need to tell a coherent story. Because if you're not telling a coherent story, because you can go on and be like, all right, we take this, we divide this by 4, we do the square root. It's kind of like Euler's constant. It's like, gets about 5 digits of the fine structure constant. Can you tell what's going on? Probably up for the debate there. Preserve it, small see it's the same. Those puts back in well, it's the I try to just go the way I try to conceptualize it. Oh, like, all right, we're some agents here, we're doing our stuff and things here. We have some framework. We're thinking about things, trying to do it in a logical method. Math seems to work. It seems to give us that U1 electromagnetic symmetry for free. That seems to be a crazy thing. Um, and then it's like, okay, you can just add in factors. That's cool. Can you get it close? And then other folks, it's like I had another result earlier where it's like, oh, this seems to have about 3 significant digits of accuracy. And then it falls off. And it's like, yeah, but the number I'm comparing it to, we have the 10 significant digits. So what am I going to do? Claim there? Because sometimes it's like, oh, this is kind of close to this. It's like, that's cool. Is it it? How much is it off by? Well, it gets like a couple of digits. How many digits do we know? 10, 12? Might need an adjustment. Maybe there's a correction factor in there. I don't know. That was basically using the binomial theorem the whole time, just basically being like, all right, we can get at least the first part. Maybe there's a second part. Now, in order to justify that, you're going to need to do that multiple times, maybe, I don't know, a few hundred times for the different measurements of the different constants in nature, see if they can actually group up rather than just a hodgepodge of random stuff. If you can have some coherent way you can start to tell a story, that's the whole goal. That's my take. How much money does Wolfram Alpha pay me? I paid Wolfram Alpha. I paid Wolfram Research a bunch of money for, I don't know, I paid for premium, I paid for a notebook and stuff like that. Uh, to be fair, hey, I'm not saying I wouldn't do. Listen, if I were to be offered a job, it would need to be the right job, but right, it's a decent place to work for. As long as you can handle Stephen Wolfram. That the biggest complaint I heard is Stephen Wolfram does what Stephen Wolfram wants. I'm like, okay, it's his company. Maybe he's wrong, and of course there are going to be times he's wrong and stuff. But hey, got a pretty good track record at building things. So, uh, they seem Joe Bauer. Now, is that a Joe Blow? Is that supposed to be? See, I know Jack Bauer. Jack Bauer magically seems to have infinite rounds in his sidearms, which it is what it is. What else do we got? I mean, that's really it right there. It's hold on. Let's just put in X kilograms. That crazy factor is just bothering me there. Okay, so you're gonna solve for X. Okay, and that's gonna give you at least the conjectured value for the electroweak symmetry breaking point. You put it down here because I think mathematically, since you're doing the square of this, you put it down there. Yeah, because otherwise, yeah, you would have to square it up there because it has that ratio there. Okay, cool. All right. Yeah, I looked at it. I think it gave you like 98 electron volts or something like that. And let's go back to our other friend. Oh, Joe, yes. Yes. No, it was oh God. Was it? No, they called him not wrong in the movie. That's right. It was Joe. I just remembered it was Joe. Yeah, that was a good movie. I like that. All of a sudden, I see those pictures of those mammoth mice, and my mind immediately went to what happened to all the smart folks in the movie Idiocracy? It's like, well, it seemed that the brightest and the smartest folks in society spent their time developing hair growth techniques as well as prolonging erections. And you're like, and you just see they got some orangutan. It's got some fantabulous like mane of hair, and then he's like wearing some shorts, and they're like measuring. Oh God, the movie's supposed to be a warning, not a blueprint, but hey, say la vie. So actually, where are we? Let's go back. Windows to the shared wall. All right. So if we put that in there, might ask, well, if we divided, but if we multiply, we'd actually delete the divide sign. There we go. Do we get anything interesting? All right, we get this number here. I was so hoping it would be something cool, because that's the thing. If you find something and you multiply, you're like, oh, you get something. That's exciting. Now, if you divide it by and you hit something else, kind of like if you take that Higgs mass and you apply whatever that was, the square root of 2/3 polylog, whatever that factor is. If you multiply it by the Higgs, you get the Z boson mass. If you divide the Higgs by that factor, you get the top quark mass. See, I thought that was a cool thing. So I had a little bit more confidence in this, but we're solving for kilograms, and we'll do the Z squared so we can get them spelled out in energy or giga electron volts. Okay. 98.566 electron volts. Yeah, no, it's the mass of a Z boson is about 90 electron volts, so we're over 8 protons too heavy there. Yeah. I mean, I couldn't figure anything out like that. Maybe there's a molecule. Might be like a molecule or something. Hold on, divide by C squared. Let's see. What's that give us? Yeah, that's the weak force range. Kilograms. Yeah, it's 110 atomic about half a molecule of caffeine. Yeah, it's not. At least I can't see anything that. Hey, if somebody finds something, by all means, please let me know. Let's see. But I get what you were saying now, Jack. It's like put water on plants. You mean that stuff that's in toilets? But no, Brondo. It's got what plants crave. It's got electrolytes. Do you even know what they are? And everyone's just like, you asked the question about the meme. How dare you question the meme? That's just the thing that we say. This is just the thing that we do. I learned that from working at. I used to do maintenance for a school that had disabled kiddos and troubled youth and stuff. And at one point, we were redoing the stairwell and stuff, and weren't supposed to have any students or staff or anything going out of there other than the people working directly on it, because you're laying down sticky stuff. You don't want people to get glowing stuff on their feet. It wouldn't be safe. And I remember I was there one day, and all of a sudden, kid comes barreling through, and all of a sudden, staff members right behind him. It's like, hey, what you doing, buddy? Well, it's like, this is the way I go. It's like, no, we're not going this way. It's like, but this is where I always go. And I remember that statement. I'm like, oh my God, that's me. Why do you do the thing? This is the thing that we always do. This is just how we go about things. And we get into routines. And we do the same thing again and again and again. It just becomes just part of who we are. What happens if that changes? Chaos. Oh my God, we're not who we are anymore. Oh dear Lord. But yeah, I usually don't get into. I'm open to a philosophical discussion and stuff like that. I mean, heck, prefer if anything, that's probably better at that. But for me, I'm just like, all right, well, we got some numbers, we got some stuff, we got some things. A lot of folks right now, I mean, heck, a lot of people are actually losing their jobs and stuff like that within science, but it's being cut and everything for better or worse. Um, we're gonna see what happens. But I'm like, I think I think a lot of the criticism I hear of academia, I'll touch upon this for just a moment as we're winding down. I think a lot of the issues that we have within academia, the things that I've heard described, don't sound like strictly academic issues. That just sounds like standard bureaucratic issues that happen in pretty much any larger bureaucracy that I've pretty much ever been a part of. Because you can have efficiency to a point, but then you start getting layers, and you get more layers, and you gotta go through this, and you gotta go through this, and you gotta go through this, and things become more complicated. That's one of the reasons why it's like I look at it and I'm like, all right, how do you calculate the mass of things? Well, taking some Fermi coupling that we only have to a couple significant digits, maybe five. Uh, and then we're going through and we're doing this and we're doing that, and it seems to get in this range. And I'm like, okay. And you hear folks, it's like, the hierarchy problem is why the Higgs boson mass is so much smaller than the Planck mass. Again, I'm not saying this is right. I'm not saying this solves the hierarchy problem, but the question is, why is the Higgs boson mass so much smaller than the Planck mass, especially if it's a squared relationship like Dr. Satharati was alluding to? I'm like, might it be because it's set as a scalar, let's say? Our only spin zero boson, whatever the heck that means, that's set so that the elementary unit of action may act. Just an idea. And then again, just thought it was cool because you go through, you do the calculations, you just look at the ratio, because this is basically that's just what you do. You look at the ratio between things, because no matter what unit you use, you kilograms. If you're to change the unit, and that's the whole point about having coherent units, is that there's some alignment here, that there is something like if a change in this in a system will lead to a change in that. However, the ratio between different things, like if you have like the Planck time in minutes, again, that's why SI is coherent, because if you take the ratios between two different things, as long as they have the same unit bases, you're going to get the same ratio. Like the speed of light, like the Planck length divided by the Planck time, aka the speed of light, to at least I would claim at least about seven so significant digits. That's a technicality, but the ratio of the speed of light should hold. That's the thing. The difference between length and time, that ratio should hold regardless of the units. Because as long as you have them in a coherent unit system, that ratio will remain. So I just found it interesting that I did that little calculation. I'm like, square root of the golden ratio? What the heck is this guy doing here? That doesn't make any sense. So I thought it was kind of cool. The golden ratio seems to pop up a lot in other different things, and or either the Lucas numbers, reciprocal Lucas numbers, the Fibonacci numbers. I mean, if it's built into mathematics, and we tend to use mathematics to model our physical world, maybe there's additional mathematics that could be useful. And that's one of the things where I think a lot of people get worried because they're like, can't use the golden ratio in physics. That's too woo. We can't have woo woo. People will be like, oh my god, they're going to get into all of this and all of this other things. It's for me. I'm just like, is it numerology? Yes, but numerology is numerology until it explains more with less. At that point, it becomes, I don't know, the generally accepted thing. Once people get over their anger, or I think was it Professor Pauly that said that something along the lines of physics advances one funeral at a time. It's like that's a terrible thing to say. It seems to be alluding to that certain cults of personalities that may have gained a bit of a following, had some past success. All of a sudden, they're like, well, these people are successful before, so let's just get around them and say all the things they're saying, except a little iteration, a little iteration, a little iteration. And that's why it's like, listen, if you go to a university and you're going to like a party with like physics students and stuff like that, especially if some of them are like grad students or PhDs or going looking for programs and stuff, it's like, I asked the guy, I'm like, hey, what are you looking to study? He's like, string theory. What made you choose that? He's like, oh, it's beautiful. It's fantastic. And I'm like, and I gotta say, like, I don't do this. It's like, no, he's put in the work. He's doing the things. Like, that's a reasonable thing. That's fine. But listen, I'm not here to tell somebody to do what to do. I ain't your boss. I ain't your mom. I'm a dude on the internet. I'm just exploring interesting things that maybe somebody would find useful. And if they happen to find it useful and you want to use something, by all means, it'd be nice to maybe give a little citation or something like that. Those things tend to be important for things. I say this when I didn't even refer to Wikipedia and for the video or the picture I used for the thumbnail. But then again, I'm a terrible person. Let's see. What is that? Jax is saying that is true, but it's when you push past what stopped us. Before that is when we grow. Yeah, it's we all make mistakes. How we handle them is what defines us. I don't know, as somebody that was so distraught, oh God, oh, I'm not perfect. I'm not perfect. I have all these flaws and stuff. It's then you realize I think we're all kind of perfectly imperfect. If you happen to be more of a believer of an almighty, it's, well, certain folks have said that, well, humanity was created in the image of God. Well, if you're going to have an X number of iterations of humanity, that means that we're all an infinite fraction of the almighty. That's kind of comforting. Again, I ain't a theologian or anything like that. Again, I'm just a dude. But things like the golden ratio, it's like, oh, you can't use the golden ratio in physics. That's crazy. That's that woo-woo stuff. It's like, okay, why? Just a mathematical relationship. That's all. Kind of like pi in a way. It's a ratio. Pi is the ratio of the diameter of a circle. That's what it is. It's just the ratio of curvature, of circular curvature. Is just the ratio of proportionality. And you see, I'm just saying, you see pi in physics all the time. Literally, the difference between h bar and just Planck's normal constant is 2 pi. You originally used h, which doesn't have that little bar thingy on the top. H is just 2 pi times that. That was what he originally came up with. And then you found the elementary unit action, aka Planck's constant, divide by 2 pi, we get our h bar, which is Planck's reduced constant because that's the unit of action. Now, the 2 pi, personally, I think of that as like the full cycle. Shout out to the fractal woman. She's been bringing that up a good bit, and she's trying to apparently go through and re-engineer a Codata's work into a more digestible format. I think good luck. Good luck, because at least according to Thad, one of the issues you run into, and one of the reasons he took the route utilizing the binomial theorems attributes, was that there seems to be deviation once you get past 7 significant digits. It's like, okay, some things we only have a few significant digits for, okay. But then it gets to the point where it's like, all right, we got like 12 significant digits here, and it doesn't seem to be lining up as well with other things. Because I can say this because now I'm an old internet wizard, I guess. The first time I went to second time I went to the Physics Monastery, I was doing some calculations and stuff, and it's like, listen, Thad's numbers are off here. What's wrong? But not only was his calculation off, the numbers he was using for the calculation were off. I'm like, what's changed? We go over there, and then we found out Codata had started to roll out their update to SI, the scientific, basically the metric system for scientific instruments and stuff. So they redefined some of it. Okay. And the reason I'm saying this is because originally the data that had for h bar, basically Planck's reduced constant and Planck's constant h, they gave 12 significant digits on Codata. They gave 12 significant digits. The error was pretty large in those last 2 significant digits. So when the update came around, they actually lopped it off at 10 significant digits. That's why h bar, the elementary unit of action, is now defined at 10 significant digits, because they're like, well, after here, it seems to be wonky. We have large error, so let's just lop it off. Cool. But I mean, that's the whole thought here, because ultimately, and listen, if we're trying to get more significant, that you can go through, and people have been extremely successful with that theory, group theory, and everything. As far as I understand, the standard model is basically it's what you get. You won your electromagnetic symmetry there. Cross SU2, cross SU3. SU2 is our electroweak breaking thingy there. Okay. And then SU3, then we get into, was it 8 or 9? I think it's 9 dimensions, because you get three spatial directions. And then from each of those 3 spatial directions, you could go another 3. So I think it's like 9-dimensional or something, SU3. Again, I'm not a quantum mechanic or something. I'm just looking for like simple relationships that's like, okay, could we plausibly explain this? And even if you get an answer, can you say it's because of this? It's like, if it came out to be h bar, but this is just a mass unit. I'm only taking the elementary unit of action divided by the 1 of action, which is interesting, because technically, if you're going to view Planck units as 1, so you get the 1 of length or space, Planck length, you divide by the 1 of time, Planck time, you're going to get the 1 of speed, c, technically. More or less. We'll leave that there. But, okay, so you've got the elementary unit of action divided by the, well, actually, to be fair, h is the 1 of action over there. I should rewrite it the other way. These are the ones of the system. This is the 1 of units. Or these are the references for the units. Pardon. Okay. Because I mean, you got the 1 of action divided by the reference for action, and then you've got your scalar boson divided by the 1 of mass. That's all squared ratio. Yeah, to be fair, if there wasn't Wolfram Alpha, because I literally just typed it in, just did a quick little thing, looked, I'm like, it seems to be about this. And if it didn't say that, then I'm like, I wouldn't have even paid attention to it at all. I'm just like, just a little quick thing. But since it said that, something kind of interesting, I'm like, all right, let me look into this a little bit more. Go into it a little bit more, actually get the measurements, go through, do it for the different measurements, see the deviation, where are the numbers homing in on. At first, we found it about 126, 126 and a half GeV, which had been predicted before. Great job, lots of hard work and everything. And then we were fine, and it's now about 125-ish or so. It's been measured a little under 125, 124 and a half, a little bit higher there. Seems to be about 125 giga electron volts on the lower half of that. Okay. This computation happens to come out to be it, or at least fit decently well with some of the data in what seems to be a way that can maybe make some sense. Again, have to sit down with some of my more mathematical friends and maybe some actual particle physicists that have studied this in more detail, just because it's like, listen, as a relationship, I can't say it seems to fit. I'll finish my little paper, cross the T's, dot the I's, all the references, the little graphs and stuff like that. Because again, it holds for 3 significant digits, depending on the measurement you take. Yeah, it's basically been measured at that. So the only real reason I can even have any real confidence, and oh yeah, basically if you take the same relationship, um, if you take elementary charge over the Planck charge and you square it, then you get alpha, the fine structure constant. Um, that was basically the same intuition that I had, and again, that's a known thing. Some people know it. That's what it comes out to be. Uh I know. Oh God, who was it? Fractal Woman had it. Was John something. She had him on, and he was going over that, and even she seemed interested. It's like all that. It's like, to be fair, that's kind of mind blowing. It's like probably would have blown my mind if I hadn't seen it about a year earlier, just because I spent time playing on Wolfram Alpha. Just what are these relationships? Blah. Just go in there like a crazy. I don't know. Maybe it's just being a gamer or something, where it's like you play games. It's like you try to do all these things. It's like whether it's Street Fighter 2 when it first go, wow, I am that old. I am Street Fighter 2 old. Like I even played the first one in the arcade. But whether it's Street Fighter, Mortal Kombat, anything, what do? Maybe you look through the manual or something like that. A lot of time you're like, down to forward quarter circle punch, Hadouken. You're doing all these combinations of different, like back, forward, down, up, flash kick, all these different things because you try out different combinations of things. And that's kind of what I did. And it's like, all right, well, I'm supposed to be a Physics Monastery intern. Let me learn all these things. Do I know all the things? No. But I've seen at least enough ratios. And we're at the point now where we also have the benefit of millennia worth of acquired human knowledge from literally billions of people that have come before us. Now we have the ability to make it readily accessible to the masses. I can get co-data measurements to higher precision and stuff like that. You go on and use a calculator that happens to be designed in a way that realizing there are issues with floating point numbers, and if you're going to round off, it's yeah. That's one of those things. It's like, oh my God, all these errors. Yes, there will be errors as soon as you run out of digits there. If you truncate it and you only go to so many significant digits, it'll give you the precise numbers for all those significant digits. And then, yeah, you don't have any more significant digits, so it can estimate there. Just note that. You're doing a calculation, you get a bunch more digits. Know where just the randomness is, because you didn't put anything in there. If it's data you have high confidence in, that's great. Sometimes maybe you'll just change a few numbers just to see what it comes up with. Because why? Wolfram Alpha gives you closed forms for these things. Let's see. Oh, yeah. It's That was when they were giving him his name because he didn't have a barcode on because he wasn't from that time. Yeah, they were putting him in the machine, and it's like, well, what was this? It's like, well, not sure. It's like, your name is not sure. Oh god, it just oh, it just they played into so many tropes and parodies, and it's I don't know. None of that really surprises me. Does it? Does I don't know. I go back over the past year, couple of years, and I'm like, yeah, I think if Dr. Eric Weinstein was right about one thing. I have no idea about geometric unity or any of that stuff, but that whole kayfabe or political circus, I think he was right on. Or at least something I think it's worth reading. My personal opinion. That's why I went through and read it. Took like 10 minutes. That's because I was reading on here. It's on the channel if anyone wants to check it out. But other than that, we've been go your real name. Again, what they were talking about with I'm not sure what you're talking about. Oh, to be fair, if it was that clip, I think I kind of overloaded them with a comparison to Alpha. Because I went over that thing because at least on the video that's been unreleased, I think it says like it's like, oh, Matthew Fox with the theory of the fine structure constant. Like that wasn't what I was presenting. Probably should just let them know. Because I showed them something and it's like, all right, well, that was new. I was technically just going over the Higgs boson mass, just being like, all right, this is alpha. If you do an elementary charge over Planck charge squared, you get alpha. So if we took the mass of the Higgs, we divide by the Planck mass, we square it, it comes out to be a magnitude that seems to be very reminiscent of the elementary unit of action. And not knowing any better, I'm like, what if it was? I don't know. Thad just assumed he's like, what if I assume this thing that gets the fine structure constant for 6 significant digits, one more than Weiler's, which is listed on Wolfram Alpha? He's like, what if I assumed it was true? What would I need to subtract it by? Happens to be like about the magnitude of the Planck mass, which is interesting. So I'm just taking that just background knowledge. It's like, well, if it seemed to work for Thad, maybe we just need to look for things. Just try looking in an interesting way. You see people have interesting thoughts, and you never know where a good idea may come from. Why? We're all perfectly imperfect, but I think we're stronger together. Why? Because we can. All right. It's getting a bit late. Y'all take care now. Be safe out there. It's a crazy world, y'all.